I have another example for you for work and how to deal with work when having energy conservation problems. And so here I have a block on a spring and it's been pushed back. That block then goes over a smooth surface for a little bit, encounters a rough surface with a coefficient of kinetic friction of mu sub k for a distance of d. And then that block goes up the hill, and the question is how far up the hill will it make it, or like what is the height that the block reaches? Okay, so I like to put in points. So I see point A will go here because I have one kind of energy. And then point B will go here as the block is moving, has just kinetic energy. After the block has encountered this rough patch, it will have lost some energy, so we'll call that point C. And then the block will go up the hill, and so we'll call this point D when it is stopped, equals 0. Okay, so the energy at point A will equal the energy at point B, but you're going to lose energy before you reach point C. And so we don't really care about point B, but we need to see what the energy at C will be. We need to understand what that energy will be so that we can then equate that to D. So the energy at A will equal the energy at B, which will equal the energy at C plus the work done by friction. Then once we know what the energy at C is, that will be equal to the energy at point D. So we need to find the energy at C first, and then we can figure out the height. All right, so energy at A is all elastic potential energy, which is 1/2 kx squared. X is the distance that it's pulled back. Then at point C, we have velocity. So 1/2 mv squared, we have kinetic energy, and I'm going to call that the velocity at point C, plus the work done by friction, which is the force of friction, times the distance that the block travels. We don't really care about the cosine piece because we've already sort of instilled a positive and negative by looking at what's happening. And the other reason is that this is parallel to the surface. It's either going to be cosine of 0, which is 1, or the cosine of 180, which is -1. All right. So what I'm looking for is this term. If it asks for what is the velocity at C, we might want to keep this the way it is, but it's really we just really want to know the energy at C, so I can put it back to this. Okay, so 1/2 kx squared, I'm going to move this to the other side, minus mu sub k times the normal force, which is just the mass times the gravitational field strength, times the distance that it travels, equals the energy at C. Now, the energy at C equals the energy at D, so that's going to be equal to mgh. Okay, at this point, it's just solving for the things that you don't know. It's just algebra, so if I gave you values, you could plug them in here. The important thing to note is that whenever you have a spring elastic potential energy, the masses won't cancel, so you will need to know the mass of the block.